Hey guys, welcome to part 3 of analyzing resistor networks. To begin with, I wanted to start you off with what are the steps when we start analyzing a more complicated resistor network. Step 1 is you got to find the equivalent resistance and the total current going through the circuit. Alright, step 2, draw in each of the individual currents on your circuit diagram. And then step 3 is we're going to use our Kirchhoff's laws to write loop and junction equations. If you understand how to do all of those things, then you will have great success in analyzing resistor networks. If you don't immediately understand them, spend some time looking at the equations that I'm writing down, and it should all eventually gel together in your mind. All right, here is the example we're doing, so find it in your notes packet. As you can see, though, I did decide to make one change to it, which is that right there. So instead of the battery being 3.3 volts, because what? Just make it 3 volts. And as you can see, part 1, or part A, asks you to find the equivalent resistance and the total current. Okay, I'm not going to go through all of that in excruciating detail, so go ahead and skip ahead or pause the video and work it out, and then I'll do it rapid fire on the screen. Well, now that we've got that out of the way, I am going to skip part B of this question, so we'll move straight on to part C, which is the bit I'm really interested in anyway. Find the current in each resistor. All right, so if you think back to moments ago, what did I say the second step was? If you remember what it was, go ahead and do it. Or if you're not quite sure how to do it from my description, then, well, keep watching. All right, now the first current I'm going to draw in is that one right there, and there's a couple of important points that we can make here. Number one is the direction of the flow of the current is determined by the battery. So if you recall, batteries have two terminals. They've got a positive terminal and a negative terminal, and the current flows from the minus to the plus. Okay, so that's why I've drawn that direction for the current. The other really important thing, though, is currents flow from junction to junction. All right, so the junctions you should be able to identify from previous videos, but right, there's one junction, there's another junction, and for a reason I'll discuss in a little bit, we don't actually consider this junction and this junction to be actually two extra junctions. But notice the thing I want to hone in on before we get to that one is I have drawn this current going from here to there and no further in either direction. The basic rule for drawing your currents is don't blow through a junction, okay? If you had drawn a current that went wee all over it, oh my goodness, if I could smack you, I would. Actually, I probably wouldn't because then I might lose my job. But hey, it's distance learning. You are safe from my smacks, turns out, but if you do that, then you're actually still wrong and you should feel bad, okay? Currents only go from junction to junction, and that's it, okay? If you haven't going any further, then you have done wrong. At a junction, the currents must split up. They must split, which means that all of your currents after this junction are going to be smaller and have to have different names. All right, so let me draw those. So the next three currents I'm going to draw are going to be those ones there. And I don't actually draw any current here or down there. Although, if I were taking this drawing perfectly literally, that is actually what I would need to draw. Okay? There is, however, a feature of this that I want to point out, which is that we should consider these two junctions to be really the same, meaning those aren't two different junctions. They are one junction. And then these junctions down here are also the same. Reason being, I could have drawn this circuit in a different way, and it would be exactly the same thing. And if I had drawn it like that, I think everybody would agree that we don't have two separate junctions at the top. We've got one junction, there it is, right there, that one junction, and then the current splits three ways. Okay, so I don't need to make up two extra currents, right, up there and down there. that would just create much more of a headache for me in the long run. The next step is we've got to name our currents. The most essential one for this type of circuit that you've got to name is the I total, all right? Anytime there's only one battery in a circuit, there's going to be one current which you can name I total because all of the current that exists in the circuit comes from that one battery. So whichever branch the battery is on, that's the branch that's going to have I total. So thus, I total goes right there. For the other three, you can name them whatever you want, right? B, C, D works fine here, but you could just as easily have used 1, 2, and 3. And now we are ready to begin writing our equations. All right, now I've set it up so that you can see we're going to write a junction and 3 different loops. The number and types of equations that you need to write for a particular problem are going to vary, but you will usually have more loops than junctions. And usually you're going to only have 1 or 2 junction equations. And then as many loops as you need to have to solve for each of the individual currents. Now, if you recall, the format for the junction equations is I in equals I out, okay? Because that's Kirchhoff's second law. And then for the loop equations, those ones are going to be of the format usually battery, EMF, minus, and then for each of the resistors, IR, because V equals IR. Okay, and then IR, and however many IRs you need to get back around to wherever you started on the loop, and then equals 0. I should say that we don't always have to include a battery on a loop equation, and later on we will see somewhere we don't, but at this point, it's probably easiest to just stick with all of our loops go through the battery. All right, and there's our first junction equation. Remember, the idea was I in equals I out, and also remember that this one, or these, quote, 2 junctions here are actually the same junction, right, because really this is more like how things are connected up, okay? There's only one connection point that those 3 branch off of. So we have I total going in based on the direction of that arrow, and then IB, IC, and ID going out of that junction, again based on the directions of the arrows. So there we have it, I in equals I out. So 3 currents go out, 1 current goes in, and that's the equation that we write to represent that. The next thing is writing our loop equations. And whenever I draw a loop equation, I like to trace the loop that I'm actually doing. So you can see I've traced the loop up there in red. And the things on my loop are the battery, resistor A, and resistor B. So when I write my loop equation, I will have 3 terms, 1 for each circuit element. So EMF for the battery, remember that's that backwards 3 symbol is EMF, stands for the volts from the battery. All right, and then minus IR, and then minus IR again. Notice, though, I'm being very careful, particularly right now, now that you're seeing it for the kind of the first time, I'm being very careful to call the currents and the resistances their individual names, okay? So going through resistor A is I total. So therefore the volts it uses are I total times resistance A. All right, and then as I move further around my loop and I get to resistor B, the volts used by it are current B times resistance B. Right? It's got to be the current through that resistor times its resistance for how many volts it uses. All right, and so at that point, I've done my battery, I've done resistor A, and I've done resistor B, and now I'm back where I started. My loop is complete, and so I write equals 0. This is going to be the format for every loop equation you will ever write. All right, the next step is going to be to plug numbers in, so let's do that real quick. So just from the circuit diagram, I would have the 3 and the 1 and the 4, right? The battery, EMF, and the individual resistances. And if I hadn't done part A, I would be stuck because I would have 2 unknowns. I wouldn't know either of those 2 currents. But up here in part A, I already worked out that the total current is 1 amp. So I'm going to plug that in, and now notice I only have 1 unknown current. that's kind of the point of writing these loop equations, is we should be able to figure out each individual current if we write enough loop equations. All right, so a tiny bit of algebra later, I've got that current B is 1/2 of an amp, or 0.5. All right, now at this point, if you feel like you know how to write loop equations, then you should pause me and see if you can do the next loop. The next loop, of course, being this, in order to figure out current C. All right, so pause me if you feel like you get it, and then resume. All right, just rearranging my own screen real estate a little bit, and drawing in dotted red lines up above the new loop I'm going to do. And you should notice that those two loops that I've just got done writing are incredibly similar. That's because they went through 2 out of the 3 same circuit elements, right? I've got my battery, I've got resistor A, and then the only difference is now this other loop takes me through resistor C, giving us 1/3 of an amp for current C. All right, now it's time for the grand finale, I think. We're going to get current D. So again, pause me if you feel like you know what you're doing, and then resume. See if you got it right. Okay. So 0.167, or 1/6 repeating. All right, fine. So that's 1/6 of an amp, turns out. Now, there's one secret here at the end, which is that we didn't actually need to write that last loop equation. Turns out we had enough equations already to solve for D, and I did not need to write this last loop equation. I could have, in fact, used instead my junction equation. Because, as you can probably see, if I take those 3 currents I solved for and I plug them back in, and I plug in my 1 amp for the total current, well, all that shows is that they add up, right? If I take 1/2 plus 1/3 plus 1/6, it is in fact going to add up to 1, which is what the total current was in the first place. So there's 2 ways that you can use the junction equation. One would be this. All right, I have solved for I total, I've solved for B and C. I'm just going to subtract to get current D. Okay, fine, that's totally acceptable. The other way you can use it is sort of like as a checksum kind of a thing, right? If you do your loop equations and you get those 3 currents, and you already found current total at the beginning, you can go back and look at your junction equation and see if they really add up. And if they don't, well, then you know you made a mistake. Like if I got that current B was, I don't know, 0.6 or something, that would add up to 1.1. I would know that I had to have screwed up, because they should add up to whatever the total current is. And obviously, if I got the total current wrong, all of the currents are going to be incorrect as well. Either way, you're going to be able to know that you made a mistake and that you ought to go back and redo your work. Okay, that should be everything you need to know for doing the homework, because all it is writing loop and junction equations. If you feel like you need more practice with this, you could look back over the video again, or you could try another example and check the notes key and see if you have worked that one out correctly. All right, thanks guys. I'll see you on the internet.